Hello, welcome to Forces tutorial number 1. Let's take a look at question 1. Now this spring is being pulled by a force of 0.6 Newton. It's connected to spring B, right, and then it's connected to the wall. Now, what we need to know is that when springs are connected in series, the tension in each of the springs is the same. So in spring A is being pulled with a tension of 0.6 Newton. Spring B is also being pulled by a tension of 0.6 newtons as well. So to calculate the extensions of spring A and spring B, we only need to apply Hooke's law, F is equals to Kx. So for spring A, the force applied is 0.6 newtons and the force constant is 6 newtons per meter, leading to an extension of 0.1 meter. For spring B, you notice that spring constant K is less stiff, so it's less stiff, okay, than spring A. This means that when you apply the same force, spring B extends further. There's more extension. Now, the total extension of the two springs is thus 0.3 EM. Now, what happens is that the effective force constant of the combination can be calculated as the K is equals to the force divided by the total extension. Since the force applied is 0.6 and the total extension is 0.3, the effective spring constant is 2 newtons per meter. Now notice that the effective spring constant is lower than for either spring. Alternatively, we can use the equation for springs in series to find out that the effective spring constant is equals to 1 over Ka plus 1 over Kb. That's 1 over 2. Don't forget to reciprocal it again to get K effective is equals to 2 newtons per meter. And that's the end of question 1. Now let's take a look at question 2. Draw and label all the forces acting on the bodies based on the scenario provided. For a coconut floating at rest on the sea, let's say half of it is underwater. There are two forces acting on the coconut. The first force that's acting on the coconut will be the force of weight. And the second force acting on the coconut will be the force of upthrust. Now, notice that since the coconut is floating, the upthrust and the weight are equal. Let's take a look at part B. A steel bob suspended at rest from a fishing line. The steel bob suspended at rest from a fishing line has got three forces acting on the bob. The first force is the weight of the bob. The second force is the tension of the string. This one is quite clear that there is going to be a tension. Okay. Now, the third force is the upthrust. Now, notice that the tension and the upthrust must equal to the weight because the forces will be balanced. And so the length of the vectors that I've drawn roughly add up. Okay, so you can see that the tension vector and the upthrust vector adds up to the weight vector in terms of length. Okay, now let's take a look at the third one, a steel bob resting on the seabed. The steel bob resting on the seabed of course has got weight. It has also got upthrust, but the last force that it has will be the normal force. Okay, so this is the normal contact force, or N. So I'll just write N here and then I'll write bracket normal contact force. Now once again, notice that the normal force plus the upthrust will be equals to the weight of the bob. Let's go on to the next question. A fully submerged buoy at rest tethered to the seabed. Now the buoy has a weight mg, but this time the upthrust is greater than the weight. So this is upthrust. In order to balance the upthrust, there has to be an additional tension pulling downwards from the point of the cable. So for this case, the tension plus the weight will be equals to the upthrust. Because the buoy is floating, in the water. Now let's take a look at the next example, which is a helium balloon pulled along by a child walking at constant velocity. Now notice the first thing is that the tension is acting in a very strange angle in this direction. Okay, now how can it be that the object tension, right, is pulling like that, but the object is moving at constant velocity? Well, let's also think about how the weight works. Okay, the weight works downwards, all right, and that is holding the balloon down. There's also an upthrust that goes in this direction, upthrust. Now, what we see is that the tension can then be resolved into two components. The tension is actually pulling to the right as well as downwards. If we put this as theta, then this component here will be t cos theta, and this component here will be t sine theta. Now you see that for vertically, mg and t cos theta equals to u. But how about horizontally? Horizontally, what does t sine theta equals to? Now, what this equals to means that there is going to be an air resistance R over here. And as you know that when you're moving through the air, there's going to be an air resistance force. So these are the two examples, the two equations, okay, that will help you to decide how many forces there are acting on the balloon. So I hope you are able to do this question too. If not, please replay the example. It's important for you to be able to do this on your own. Now let's take a look at question 3. The diagram shows a long narrow tube which is empty. The tube is then filled with water to a depth of 0.7 meters and then inclined. Determine the pressure at point X when the tube is filled with water and inclined. Now, when the tube is not filled with water, the pressure at point X will be atmospheric. When the tube is filled with water, the pressure at point X will be atmospheric pressure plus the water pressure, which is H rho G. Over here, when the tube is inclined, the pressure at point X will again be atmospheric, and then will also be H rho G, but this time the height is different because it is only the vertical height of the water that counts. Alright, the slant height, the diagonal height doesn't matter. So let's take a look at what happens when the pressure at point X, the tube is filled with water and then inclined. Now first of all, we need to know what is the H2. 0.70 meters over here, and the tube is at 35 degrees. So this one will be 0.70 sine 35, which is H2. Okay, so we fill in all the numbers. Atmospheric pressure is 100,000 pascals. The height is 0.7 sine 35. The density is 1020, and G is 9.81, leading to 104 kilopascals. So this is question 3. Now let's take a look at question 4. In order to pump water up a pipe, a strong vacuum pump is attached and tries to suck water up the pipe. What is the maximum height that the water can be pumped using this method? Now, since this is a vacuum pump, maximum height will occur when the vacuum pump is operating at a maximum strength. That means the pressure at the top here will be a vacuum, which is 0 pressure. Okay, so the vacuum is quite unrealistic and it will never happen in real life, but the pressure at the top is 0. Okay, the pressure at this point will be 0. Now, remember that pressure increases as we go down the tube. So the pressure at this point will be the pressure on the top, which is 0, plus the pressure of the water, which is H rho G. Right, this part is H. But notice that also over here, the pressure is also atmospheric. Alright, so we realize that these two pressures must be the same. Atmospheric pressure must be equals to the vacuum pressure at the top plus H rho G. So we can say atmospheric pressure is the same pressure as the pressure at the top plus the water pressure of the pipe all the way down to the bottom. Okay, and now rearranging the formula, we can get this pressure at the top is pressure atmosphere minus H rho G. Okay, and then we can then fill in all the details to get H is 10.2 meters. So we realize that using a vacuum pump is not a good way to pump water upwards. How come? Because the maximum height is 10.2 meters, which is not really even 3 stories tall. So instead, what you should do is compress the air at the bottom, or instead high pressure at the bottom, okay, can raise the water higher because there is no theoretical upper limit to the pressure, okay, at the bottom. Whereas the pressure at the top can only be 0, and it can't go any lower than 0. So that's question 4. Now let's take a look at question 5. A rectangular block has a cross-sectional area of half a square meter, which means to say this area at the bottom over here, this area is 0.5 square meters and mass 420 kilograms, which means that the weight of the block will be 420 multiplied by 9.81, which will be the weight. What is the depth to which the block sinks when you place it in the water? Now, the weight of the block must be balanced by the upthrust of the water on the block. Now, the upthrust of the water on the block will be the volume multiplied by the density of the water multiplied by gravity. Alright, so if the block is floating, that means that upthrust must be equal to the weight. And so the volume of the block, V rho G, must be equal, the upthrust of the water, V rho G, must be equal to the weight of the block, mg. But what about volume? Now the volume of the block will be the cross-sectional area multiplied by the length of the block. Okay, so that's how we go from V rho G equals mg to AL rho equals m. So fill in all the values over here and we get L is 0.854. And this is the end of question 5. Now let's take a look at question 6. A sphere of a volume of 2.25 times 10 to the power of minus 6 is made of styrofoam of this density, is anchored to the bottom of the tank by a string. Calculate the tension in the string. The first thing that we've got to do for this is to actually draw the weight, and then we draw the tension, which I draw to the side because I don't want to completely cover everything up. This is the tension, and then there is the upthrust. The upthrust force will be equals to the weight plus the tension. So we know that upthrust is equals to mg plus t. Okay, so how shall we fill in all the details? The upthrust, okay, U is equals to V rho G. So we fill in the volume of the sphere, the density of the alcohol, and gravity. Now the weight will be mg will be mass, the volume times density times gravity. It says the volume times density will be equals to the mass of the ball. Right, so the mass of the ball, the weight of the ball is 0.001104. So if you consider the forces vertically, upthrust is equals to weight plus tension. The tension will be upthrust minus the weight, and the tension must be 0.0166. So let's fill in all these details and you'll see how it works out together. So this is 0.0166 newtons divided by the string. The weight of the sphere will be 0.001104, and added together, this will be exactly the same as the upthrust, which is 0.01766. Okay, newtons. So this is how the forces work together. And that's the end of question 6.